सारी की कराई इसकी जी जी ऑनलाइन
Hello, this is mic testing. This is mic testing.
दिन वो एडमिट करने में आप कर रहे हो? हाँ, खुद से ऑनलाइन यूट्यूब पर उस पर नजर रखनी है। यूट्यूब पे भी नजर, यूट्यूब पे भी। अब यूट्यूब बंद कर दो क्योंकि उसमें चार्जिंग है, मैं खोल लेता हूँ लेकिन उसमें नेट नहीं है, जाएगा। जा रहे हैं।
Now this is testing.
क्या मसला हो रहा है जी?
सर क्या है वो सर की प्रेजेंटेशन इधर रखने के लिए।
ओके, यू कैन स्टार्ट.
Hi all. Hello, online participants, can you hear us? Give a thumbs up, guys. Okay. Good. Okay. Although there's no need of an introduction to Dr. Jamal Rustami, he is leading professor in rock mechanics. He's here not only as a professor of rock mechanics, but he is here as a vice president of International Tunneling Association. We might be, some of the faces might know us. Pakistan Trenchless Tunneling Society, represented by so many people here, they are trying their best to introduce the tunnels in Pakistan, not only for the roads, railways, and motorways, but more of urban also. So we need these tunnels down the road. Is our metropolitan cities, they require these tunnels. And we are asking the world experts to introduce us to that venue where we can get some expertise from the world to let our audience, our students, and our policymakers know that what are the benefits of the tunnels underneath and how we can utilize the underground infrastructure development. So without much delay, I'll request Dr. Jamal Rustami to take over.
Okay, assalamu alaikum. Good morning, everyone. Thanks for coordinating this meeting. I know that it takes a lot of energy to put a seminar together. I appreciate the time that the faculty and dignitaries are spending to be here today. And I hope that I don't disappoint you. I'll try to give you the different perspective. Before I start talking about the topic, as Vice President of ITA, I wanted to emphasize on something. In 2022, when this new executive committee was elected in Copenhagen, the following day we had a meeting. And one of the topics that we wanted to discuss was, what is the slogan of ITA, International Tunneling Association? I thought, and in the agenda we had put down 5 minutes or 10 minutes for that. I thought, right, go through it very quick and be done. It took us about 2.5 hours to come up with what is the slogan for ITA. And after going back and forth, we came up with one simple phrase: underground space for better life. Better life for who? For people. So we're not just making a hole underground. These holes, these spaces have a purpose. They have to make people's life better. They have to reduce the traffic congestion. They have to give you water. They have to take the sewer away. They have to give you storage. They have to essentially make people's life better. But that's our, focus on this movement. Not too complicated, but we have a mission. We have a purpose. So in this presentation, I'll essentially talk about TPMs, and I'll explain why. Go through the introduction. I'll talk to you about some historical perspective. Give you some, discussion of the TPM classification. What are they? What's the purpose? Then some of the discussion, recent development, and glimpse of future outlook. So the first question is, why are we talking about TPM? The reality of it is that in today's world, about roughly 85% or more of tunnels in the world are excavated by tunnel boring machines, excluding the mining. And pretty much they're the best options or the choice for any tunnel that's above 1.5 to 2 kilometers. That range depends on the application, it depends on the work culture, depends on workforce, and everything else. So in that range, above 2 kilometers, I mean, it's not a very good choice to go with conventional tunneling. This is the fastest method of tunneling. The world record in 1 day is 165 meters in 5.5 meter diameter in Australia. Just think about it. 165 meters of tunnel in 1 day. And that 1 day could be impressive, but if the rest of the time you're trying to do repair and other stuff, it's not good. So the best, one of the world record in tunneling per month was about 1,200 meters. So over a kilometer per month. And now this is becoming very regular in the 5 to 6 meter diameter range. At this stage, in pretty much any type of ground that you can think of, TBMs can do 3 to 10 times better than conventional tunneling. I mean, that tells you how potent the system is. And especially for developing countries, right? This is critical because we've lost a lot of time. And we have to have this infrastructure to improve people's lives today. We cannot delay it. It has to happen very quickly. Nowadays, running a 40 meters a day with a rock tunnel, TBM, is pretty normal. So if you say that, in a project that you're doing 40 meters a day, it's good, but it's not going to impress anybody, right? It's becoming normal. And a soft ground tunneling, like metro tunnels in soil, doing about 15 meters a day is becoming a norm. It's about 10 rings, 10 concrete rings per day. So can you imagine, this is becoming the norm that you can do about 400 to 500 meters a month of metro tunnels, right? Just think about the potential that it could actually unlock. Another good advantage is that we have to be careful and mindful of people's life and health, right? Safety and health. These operations with TBMs are pretty much the safest way that you can do tunneling. So people can go to work and go back home the same night, right? And pretty healthy, so they don't have to worry about silicosis and all type of health issues. And ultimately, at this stage, we are capable of going through pretty much any ground you throw at us. Soft ground, hard rock, mixed ground. In the past, it was a nightmare. You could not go from soft rock or soft ground to rock. Nowadays, not a problem. Switch between the two, we can go through it. So although TBMs are supposedly called, modern marvels, the reality is that goes back about 170 years ago, where Brunel and General Beamon wanted to go under Thames River with TBM, and you can see this is the general scope of the machine, the rotating cutter head and so on. And then at the same time, roughly about at the same time, about 20 years later, this other machine popped up in the US. So it goes back a long time. But this didn't actually become a reality till 1950s, when James Robbins put together a machine in Ohio and dug a tunnel with disc cutters, and boom, that was the technology then. So this is one of the modern machines, right? It has disc cutters on it. Let's see if I can essentially. It has disc cutters, cuts the rock, material falls down, picks up with the scoop, send it back to the conveyor. You've got your tunnel. Pretty, nice and easy and nice flow. Of course, this is a machine, this is an open machine with the grippers, right? That can grip the wall and push the machine forward. Even a more modern machine that you can see here, general, essentially, components are the same, except that in this cutter head here, you can change the cutters from behind. So you don't need to send anybody up front in unsupported areas. It's very quick, very fast, and very safe. Of course, we didn't stop there. The machines that had to go through soft ground, because of the stability issues in soft ground, we had to go with shields. So you can see different type of shield machines that have been introduced over the years, up to the point that this is pretty much what's called a double shield that has capability between cutting rock, passing through the fault zone with segmental lining and whatnot. Pretty fast, pretty amazing. But to talk about general classification of tunnel boring machines, this is a chart I drew up a few years ago, and I still use it. It tells you the story. If you think about TBM, you can actually have rock tunnels or soft ground or soil tunnels. Rock tunnels, if you are in pretty good rock, you can use open type machine. If you're uncertain or expect to go through a lot of fault zones, you can use single sheet machine. Or if you want to install ground support, what's called a one-pass system to install the final line, you can go to the single sheet machine. These machines up here are primarily for rock, but they're so-called open mode. By open mode means that you cannot maintain face pressure and you cannot maintain water in the ground. Water flows through, but that's fine. But down below here in the soft ground glass, of course, except for one small group that's called digger shield, which is essentially non-circular, push off the segment, special machines that are really not very common anymore. You have two major type of machines for soil that is fine grained, like clay, silt, and this type of material. You can use earth pressure balance machine with a screw conveyor, or for the coarser grain material like sand, gravel, and rock, you can use what's called the hydro shield or slurry shield. Again, the system allows the slurry to go into the face, maintain face pressure, keep the water out, and then extract the material that has been excavated. Of course, when we talk about a tunnel that is 5, 10, 20 kilometers, you are not going to be in the same formation. You have to have hybrid machine that can actually switch between the modes. So over the years, they have actually developed hybrid machines that can actually go between the systems, be optimal for each system. And of course, if the water is an issue, which is becoming a very common theme, that even if you're in rock and the ground is stable, if you allow the water to drain, it would create surface subsidence. So in a lot of projects recently, when we are even in rock, they try to keep the water out. So they're using a combination of these machines with the rock cutter head. And nowadays we can actually tunnel under, the world record is 17 bar of pressure. 170 meter of water head, we can mine through it. You watch us walk in, walk out, it's like, a submarine, right? But that's the capability and classification of the TBMs. Now, let's see. I had a couple of videos, but in the interest of time, I bypassed them, but you can actually look at the operations of these machines on YouTube or a lot of other media. But anyway, I encourage you to take a look at it. It's really neat to see how these systems operate. So if, again, going into details, you see a main beam machine, which was original TBM, which has the cutter head support, the main beam that hosts the conveyor, and also is the structure to transfer the load from the gripper over to the machine, right? This was and is the open type machine, and it's good for, per se, a stable ground in rock where you don't have water issues. This is a picture from Norway. It's become a landmark. Some people take a joke at it and call it getting stuck between the rock and a hard place. The smaller machines, you can actually have small machines here. This is the smallest that I've worked on. It's about roughly 2.2 meters in diameter. That's really tight. Just to let you know, you see this wood plank here? What do you think that is? Right on top of the conveyor. The space is so small that that's the operator's seat. I mean, imagine sitting on top of an active conveyor for the whole day running a machine. So it's a very tight operation. And this is the final product. And of course, even in this situation, if you don't do it right, you could create a sinkhole. This machine, as small as it was, created a sinkhole right next to a highway. So operation of the machines, this is looking through the sinkhole, you could see the cutter head. So there are a lot of intricacies in operating machine, even in the smaller one. And by God, I tell you, the most complex part of TPM operation now is the diameter below 2.5. Very difficult because you don't have enough space to operate. In larger machines, the largest open machine is this one in Niagara Falls, which is about 14.4 meters in diameter. You can see the size of the machine relative to the guys standing in front of it. It's like a 5-story building. Imagine a unit that cuts a 5-story building in rock and moving forward. It's pretty amazing. Of course, you may have heard of the channel tunnel between the UK and France. Again, they were excavated by tunnel boring machines. It's a single sheet open mode. As you can see, the machine installs a segmental lining behind it. They're all sealed, so you can go underwater without much of a problem. The machine pushes off the segment to go forward instead of the gripper. This is a double shield machine which has both the gripper and the shield system. Allows you to run the tunnel in the hard rock without any segments if you don't need it. And when you get to the fault zones or bad ground, switch, install segments, push off the segments to go forward. And a couple of things that I wanted to also mention here. You see these ports here, they're for actually probe drilling, which allows you to actually drill about 50 to 60 meters ahead of the face, see what's going on. If there's any issue, we'll let you know. The back end of the machine, as you can see, the machine can go off the gripper, meaning that in good rock, keep going, don't stop, keep going. And in bad rock, right in the tail shield here, you can install segmental lining, precast segmental lining, to essentially protect the ground and push off of it to go forward. This is a larger version of that machine for a project in Spain, Abdulaziz. But one of the trends in the world, which actually you guys might run into it pretty soon, I was in Lahore a couple nights ago, under Chahi, congested area, and parking is an issue, right? A lot of places in the world now are building underground garages right under congested part of the city, which is actually the historical place that everybody wants to go, right? And you need that space. You cannot create it upward. You have to go downward, into the ground. However, for stations, metro stations, garages, and other applications, you need a bigger space. But if this becomes longer, then you have to switch to TPM for, longer tunnels. Now, in the past, when we were talking about large openings, there was an argument that whether we should do in 2-stage, meaning do a pilot and ream, or whether we should do in 1 stage. The main issue was the ground stability. And by God, they have tried it. This is a machine that was tried in 1980s, 2-stage excavation up to 12-meter diameter. However, due to many complexities, they did not actually follow through with this. And the main issue is ground stability. You're civil engineers, I'm positive many of you know about rock mass classification. Even if you don't, we briefly discussed rock mass rating or rock mass classification. You go from one end of this chart, which is 100, and then 80, 60, 40, 20, and so on. If you are in this area, it means that you're in very good rock. If you go to 60 to 40 is fair rock, can hold up. Below 20, you're dealing with soil type material. So that gives you a perspective of what is rock mass rating, right? So you have very good rock on one end, poor rock or soil on the other end. And look at the span here, right? This is the span of your opening, be it tunnel or anything else. Now, if you're in this zone, it means that your opening doesn't need any ground support. It will stand by itself. If you're up here, it means that you're going to have immediate collapse. What is the implication? Down here in this zone, you're pretty much open. You can use open type machine. Even in this group here, you can use open type machine to up to 10, 12 meter diameter. But here in poor ground, even 1 or 2 meter diameter, is immediate collapse. You don't have any time. What does that mean? It means that you have to go to shielded type machine. So that's the rule number one of machine selection. How do you select between open machine, double shield, or single shield? You have to look at the ground stability based on your geotechnical investigation. So there are other charts that would help in selection of the machine. Again, this is the rock mass rating. 100 means very good rock. Anything below 20 means that you're pretty much in the soil type material. And you can see different type of machine from open, double sheet, single sheet, and even pressurized phase. However, as I mentioned, water is the tricky part in the whole thing. If you have to deal with water, irrespective of the stability of the face or the roof and the wall, you have to deal with water separately, meaning that you have to keep the pressure of the face, prevent water from draining inside, because otherwise, no matter what, you're going to have surface suppliness, right? So this is an example of a project in Sweden, Holland says. This is a project that has been in construction for around 40 years. They went with machine, had plenty of water coming in, it inundated the tunnel. They pulled the machine out, went conventional, again problems. They had to do pre-excavation grouting to contain the water. Slow as hell, they couldn't get anywhere. They switched back to machine, conventional, and ultimately this machine could finish the job. This is a slurry type machine, hard rock cutter head, could keep the water at the face, no water going in. They finally finished the project with this unit. There are other charts that are available from Germany, from France, from US, from Japan, and ITA has also got some guidelines on machine selection that you can find. Which machine is best suited for what type of ground? So these are the things that you can get through. However, as this slow motion is going, the key issue I want to mention here is that machine is a small part and the front end of the tunneling system. The backup of the machine is as important, if not more important, than the machine. So the machine selection tells you how to deal with the material, how to excavate it and take it out, but the backup is what makes it happen. In other words, TBM is a tunneling factory. So how do you deal with a factory? If you have an assembly line from point A to point B to point C, everything has to work. That's the importance of the backup. You know, in TBM operation, we have a definition for, how much time we are actually tunneling. That's called utilization factor, right? The amount of time that we are tunneling, excavating the material compared to the total time is called utilization factor. Typical TBM utilization is about 20 to 30%. What does that mean? Operations of the TBMs are 24 hour per day, because when you have that much money invested in the tunnel and the equipment, you don't want to go back home and sleep and come back the next day. It's 24-hour operation TBM, right? So 20% means that out of the whole day, you only mine 5 hours, right? And the rest of the time goes to what? To maintenance, to delays, to breakdowns and everything. What part of the system deals with that? That's the backup. So I'm going to emphasize that, yes, selection of the machine, design of the cutter, all that is important, but 70% of the time is spent in the backup and the logistics. It has to be really well planned. Otherwise, you lose a lot of time. We have cases where the machine utilization drops to about 4 or 5%. What does that mean? 4% of time you're mining, 95% of the time somebody is doing something, right? And unfortunately, I must open up to that. In developing countries, that 95% or the breakdown and downtime dominates by a big margin. And we have to work on the logistics to make it happen so that we can actually reach to the international norms. So again, another setup for the machine, you can see the backup gantries where you have the power, you have the hydraulic system, you have the transport system, ground support installation, ventilation, water drainage, everything is happening in the backup. So when we talk about TBMs, keep in mind, backup is an integral part of it. It's not a separate entity. All right. Moving forward, this is like the backup I talked about. It's not just inside the hole, inside the tunnel. It could be extended way up at the surface, like for a so-called slurry machine, where your material transport is done by a slurry, water or bentonite mix. You have essentially a slurry, fresh slurry coming in, going to the face, picks up the material, comes out through a couple of booster pumps, goes out to a separation plant. Now, I'm not kidding, I'm talking about a plant that could be probably twice the size of this room, to separate the material from the slurry and send the fresh slurry back in. So the backup system could extend all the way to the surface, and it has to work. Otherwise, if there is any disruptions, the entire system stops. This is a typical slurry machine. As you can see, the slurry lines coming in behind the machine, following all the way through. So let's take a look at some of the recent development and future trends. Now, in a typical TBM operation, you have to essentially go in and inspect the disc cutters every shift, at least once a day. Okay, as long as the machine operates, every shift you have to go make sure that disc cutters are fine and working, and that takes time. So one of the things that has happened recently is to develop a system that can monitor the disc as it cuts the rock, so you don't have to inspect it all the time. The quality of materials for the disc cutters are actually hard-facing to prevent abrasive wear has gone up drastically in the past 10 years. Machines are now fully computerized. You're taking a lot of data in, and you can pretty much monitor from all the way to the cutting head to the end of backup. Even the separation plant right now is at the operator's fingertip. A lot of machines with all these computerized systems have self-diagnostic capabilities. So instead of checking everything by a mechanic, the machine can give you preventive maintenance warnings that, hey, this is happening in this section. So as you plan for the day, you know exactly what the issues are, can deal with it. All of this goes towards what? Towards the utilization. You are trying to up the utilization, meaning that you get more footage per day. Probe drilling is now becoming pretty much a standard on the machine. This is fairly recent. In the past, probe drilling was an option. Nowadays, most owners require probe drilling because they want to see what's coming ahead. The consequence of not having it is that you're driving pretty much blind, and if the machine gets stuck, the cost is enormous. Just to give you some ideas about the cost, a typical metro tunnel is about 6.5 meter diameter. The cost of site is, depending on where you are, is anywhere from $200,000 to about $300,000 to $400,000 per day. Let's think about that. $200,000 to $400,000 per day. So if you drive 15 meters a day, right, that cost is broken down by 15 meters a day. It's a reasonable number. But if you do 2 meters a day, it means that your tunnel is now $100,000 a meter. You can't afford it, right? So it's really critical to make sure that the production is consistent and you get good production. So probe drilling allows you to reduce the risk and eliminate the unknowns, especially related to fault zones and water. A lot of machines are now fitted with grouting system. What does it mean? You probe drill ahead, 50 meters ahead, and the water keeps gushing in. What does it mean? You're running into a high permeable zone. So you can actually stop the machine. It's better to stop the machine. I'm telling you, I've been in some projects that has been a total mess. When the water starts coming in, and if you hit it, you've already lost the battle. You're going to lose a couple of months just trying to fight it. But if you hit it with a probe drill, right, and know that There's a water-bearing zone ahead of you. You can actually do probe drilling around the tunnel and pre-inject grout to stop the water, right? That's the best way to handle it, and you can actually do that right now. It's funny that nowadays we can actually have machines with changing diameters. It's fairly complex issues. We've been able to do it. There is a trend towards the machines that are 15 meter or above, because the demand for motorways in cities has been increasing drastically in the world. And a two-lane highway, you require about roughly 2.5 to 13 meters to 13.5 meters, that range. But for a three-lane highway, single deck, you need 15 meters. So that's the driver for that class of machines. We are going to very complex ground right now, and of course, there's a trend to reuse the muck for aggregate. You can actually either sell it or use it in the tunnel. So these are some of the details of the trends I mentioned, like the disc cutters that have the system that can monitor the rotation of the disc. If the disc stops, you better stop and go deal with it. But if you see that it's wearing on a normal rate, you can essentially, the machine is going to give you a warning that, hey, watch out for this number 4 or 5 or 20. And then in inspection, instead of spending time to inspect all, we can zoom in, look at the particular problem, and deal with it. As far as probe drilling, this is the probe drilling. You can do probe drilling through the shield or through the cutter head. We don't like to do probe drilling through the cutter head primarily because if you break a rod, then you have to go through the steel cutting through, and that's very difficult. And it causes a lot of headaches. So you can see these probe drills, different probe drills behind the machine in different type of machines. And then they can actually create a sealed membrane for you in the ground as you tunnel through. This is Arrowhead project in California. Again, in certain zones, they were required by contract specification to do probe drilling the entire section because the problem was the drawdown of the water could cause surface problems. So even though they were in rock, they had to do this. These are the twin machines for that Arrowhead project, and again, capabilities to do probe drilling and pre-excavation grouting system. With this type of machines, especially if you want to maintain water pressure at the face and use a screw conveyor, this is what happens to your screw conveyor because of the abrasiveness of the material. So you have to watch out because if the screw conveyor wears down, you cannot maintain face pressure, meaning that the water will actually overcome the pressure drop. A couple of pictures of these super large open TBM. This was used in Niagara Falls. Largest plant in shale, so essentially they had issues, and installation of ribs, steel ribs, was considered in background. The machine was supposed to be originally going based on roof bolts and maybe occasionally going with ribs. But in reality, they had roof faults, and it created a lot of issues. As you can see, even with heavy steel ribs, they could not hold the ground, and they had faults. And you see, as the machine is going forward, even with the rib, it would still, cause instabilities, and the ground is falling before you can even deal with it, or do shotcreting or the installation of the wire mesh. But there are ways to prevent it, right? This is an example, and I put this in because I know that you're dealing with Neelam Jillam, and rock burst was an issue. So this is not unique to you. I've worked on a few projects with that issue in actually Vancouver, Canada, with rock burst. And also this is a project with heavy rock burst in Andes in Colombia. A very famous project, almost project. And to contain the rock burst, they had to invent a whole new system, which is called McNally system. So this gives you a feeling of what See what's happened is one breaking. Right? If it wasn't for the revolts, ground, this is a ground which anyone would teach or kill that gap. It's because of the lateral the stresses that manages magnet, you know, stresses in the roof. However, in this system, economic system, we could actually install these slants or group of rebars inside the component. As the machine goes forward, it will deal and release the slants, like the rebars. Then the piece installed groups, with arch and go forward and be safe, right? Imagine this is a pretty strong rock. It's not a shale or really bad rock. It's really a strong rock, but because of the stress concentration, it creates rock bursts. In Yangtze River tunnel in China, there's caused some fatalities actually. If I'm not mistaken, around 10 people got killed because of the rock burst and a lot of delays. However, there is a solution for it. These are some examples of rock burst almost tunnel in Colombia, because in these situations, despite the fact that they had roof support, the extent of the rock burst up in the roof was so much they would actually collapse, meaning that even the roof bolt and the entire system will collapse down. But again, there are solutions for that. This is a case recently, actually, it won a ITA award last year where the TBM size went from 11.6 to 9.9, so about 1.7 or so difference in diameter in the tunnel. As you can see, this is how the cutter head was designed. The specific, inserts, it excavated, but at the end of first section, stopped the machine, took out these individual inserts, right? These guys were taken out, and then the machine was reassembled into a smaller diameter. There are a lot of complexities related to this issue, not only as far as the cutter head design, it's also a complexity with the backup system, because backup system is typically the choke point when you change diameter. But you can see the result here, the change in diameter, right, as per requirement of the project. So this is happening now. As far as the highest water pressure, this is the project again in the US in Lake Mead near Las Vegas. They operated the single shield slurry type machine under 17 bar of pressure. It had the capability, what it logged was 15. And imagine if you need to go and change the cutters, right? You have to take special provisions, go with compressed air, divers have to go in hyperbaric conditions and maintain the machine. Fairly complex situation. And when the rock was good, they could seal it off and then drop the pressure to atmospheric pressure and operate. So one of the questions is, why can't we go over a 15-meter in rock? The limit is not the rock, not the machine, it's the disc cutters. Because the bearings of the disc cutters in the outer gauge would get overheated and they would jam. So that's one of the issues, and we're working on it. However, the general trend has been to go to larger TBM diameters. You can see the largest machine up until mid-90s was in 10-meter range or 10, 11-meter range, and then it started going up by the demand for the motorways. And up till now, there is a design for a machine from Moscow. They build it, but 19.5 meter. The largest machine I'll show you is 17.6. So you can again see the trend of going to larger diameter TBM. There is a design for even over 20-meter diameter for a project in Istanbul, but again, it's on hold. This is by Hercules. The largest rock machine that has been built and successfully finished was in Georgia. This machine is a hard rock TBM with EPB conditions, essentially maintaining water pressure at the face and the shielded system so that the collapse could be contained, and they are actually installed a segmental lining behind it. This machine pulled through about a year ago, successfully finished the work. It's a Chinese Craig unit. The largest ever built TBM was the one in Hong Kong, going from an artificial island to the airport. Twin machines, this is the largest one on this side, 17.6 meters. I mean, just imagine 17.6 meters, pretty much the size and width of this room. That's the size, and of course, look at the launch shaft and how it's built. This is also showing, this is pretty much something that has happened about 10, 15, past 10, 15 years in China, where, especially for road tunnels, they do precast sections and build the tunnel, the road deck right behind the machine. So the transport mode is through trucks to the back of the bridge and then to the backup of the machine. So what's happening, you can see the backup of this machine is giant, like a 6, 7-story building, right? And again, going through the artificial island and pulling through. This is, again, a close-up of that machine. However, working in these slurry machines, especially for maintenance, is not a pleasant thing to do. You know, you gotta go into the mud, try to do maintenance. So in order to avoid that and avoid hyperbaric interventions, in the past 10, 15 years, they have built a way that you can go inside these spokes in atmospheric pressure, do the maintenance. So each of these cutting tools have their own airlock. You can activate the airlock, pull the tool back in atmospheric pressure, change it, put it, extrude it, and continue the operation. Again, this is another one. This is a 15.4 meter diameter TBM Hurricane, which was used in China. At the time, which was 2010, this was the largest machine in the world. Now we have superseded. But this, atmospheric intervention was put together then. By gosh, I've been into these spokes. Despite what you see, it's really tight and scary. If anybody has any phobia, it's going to be very difficult to go in and do the work. With the EPB machines, again, the same thing. Is earth pressure balance machine. Is the system that was used in Hamburg with 2 counter-rotating cutter head with different screw conveyor system. One of the issues with the EPB machines is that in the clay formations, it could clog the center because the rotation speed of the big cutter head is about 1 or 2 RPM. Now, when I say 1 or 2 RPM, just imagine what is the speed of 1 RPM, right? Very slow. And as the machine is pushing forward, it would essentially compact the clay at the center. It would actually radiate out and clog the machine, it chokes the machine. So with this type of system, they try to actually use the smaller diameter in counter-rotating mode at higher RPM to prevent this issue. The largest EPB in the world was this machine called Bertha. It was used in Seattle. Pretty amazing job altogether. Neat, because this machine, 17.4 meter diameter, went right under downtown Seattle, when all the high rises are, the headquarters of Amazon and Microsoft and so on. And of course, the machine had some problems at the beginning. It ran into some situations. You can see the size of the machine, right? Had some situations with the cutter head and bearing. They had to stop the machine, sink a shaft, remove the cutter head, change the bearing, put it back in, backfill the shaft, and continue. In the beginning, machine had problems about the first 300 meters. And just sinking that shaft and changing the cutter head and modifying the bearings cost them about $300 or $400 million, just that one repair. So it becomes very costly. Nevertheless, when the machine passed through the sand and got into clay and did its job, it's amazing that the maximum subsidence that was recorded was around 12 millimeters. I mean, just imagine a machine of this size going under a downtown all the geotechnical complexities, and they could maintain 12-meter subsidence, which is pretty much an engineering achievement. In Singapore, going through clay and granite blocks is pretty much the nightmare of tunneling. So you have the worst of soils and the worst of rocks. So going through that, they had a lot of difficulties, so they came up with this machine that is hybrid system between a screw conveyor, EPB, and the slurry shield system. So it's called variable density. So it can go with a slurry system in certain rock conditions, and then switch over to EPB in fine gray soil. However, the most complex tunneling in the world was in Bosphorus tunnel in Istanbul, in Turkey. These guys were not the largest diameter. They were not the highest waterhead. They were not the most complex ground. However, when you combine all of it, this is the most complex tunnel in the world. So you can imagine, this is the alignment, right? Going under Bosphorus, so open sea, going through shale, and then these basaltic intrusions, so mixed phase conditions, then going through all of this mess and heading this soil, which was clay, silt, underwater pressure, and going through the mixed ground here, these sections, and this section, meaning cutting rock and soil at the same time, and then pulling over. And ultimately, again, the water head was an issue in the entire line. So they pulled it off. Hats off to them. Very good job. Again, this is the machine in Madrid, EPB machine, but they run into a lot of rocks, as you can see in the face. This is block of granite. Madrid is based in granite. And running a soft run machine in a hard rock face is fairly difficult, despite the fact that it had disc cutters. Still, abrasion was very severe, but they pulled through. Also, how are we doing on time? I think we have another, 15 minutes? About? Yeah. Okay. So now, if you think about the application, circle is probably not the optimal shape for a lot of applications. So over the years, there has been a lot of discussions about, do we use circle or do we use other shapes? These are the machines that have been invented and used in Japan. But over the years, also, they proved that it's very difficult to operate, so you don't see them anywhere in the world. And even in Japan, they're pretty much done. However, the box-shaped machines have already, gained ground in recent years. So these are some of the Chinese, machines. This is for a double-track, single-tube metro tunnel, right? Just to be optimal shape for the two tracks. This is about 6.5 meter high, about 10.5 or 11 meter wide. Just gives you the envelope for two tunnels and two trains going back and forth without extra space. So you can see Chinese have been working on this quite a bit, and going for non-circular opening, given the application. And the machine that has been fairly successful is the one that you see here. They've used it several times. Again, this is pretty much trying to optimize the shape for the application. And they've extended that to rock as well. I mean, look at this version that has disc cutters for cutting rock, and in between the curvatures, cutting with pick cutters with this drum. And as you can see, they pull through. So there is quite a bit of emphasis on that. And it's not only for this tunneling where you install the segment behind the machine. This is the version that can be doing pipe jacking, meaning jacking this the lining with the machine into the ground. And of course, there is a limited range of how far you can go with it. Installation of the segments in this non-circular openings is fairly challenging because in the normal circles, you go to a radius, install, and you're done. But here, you have to go to different radiuses and install the segments. And to give you the intricacies, we're talking about the segments that could be anywhere from 250 millimeter to 600 millimeter thick, 1.5 to 2 meters wide, and the section, the curvature could be 4 to 5 meters. Each one of them could be somewhere in the order of 10 to 15 ton. Okay, now you're lifting it up, moving to the position. It has to be installed within less than millimeter accuracy, right? So it's pretty delicate to make sure that you don't hit the pieces together because they will actually damage it. And the gaskets that are maintaining the seal, water seal, they also have to go lip to lip, very gently and compressed. If you rub it, it would tear off the seal, meaning that you're compromising the water stuff. So they have actually developed a system for installation. For any road tunnel or for any metro tunnel, it's by code, by law, or by international standard that at least every 500 meters you have to have a crosspass. In case there's an accident, people can come out, go across to the safe zone and stay. And there are machines now that can actually go along the tunnel, punch through instead of manual excavation, because right now, pretty much the standard is the manual excavation. We're trying to make that also automated and mechanized. There are also machines that could mimic cut and cover or, let's say, immersed tube tunneling. For passage under rivers or under, let's say, lake beds, if it is at the surface, instead of cut and cover or immersed tube tunneling, you can use this type of modified machine that can be launched out of a cofferdam and excavate the bed, install the segmental lining, and then you can anchor it down into the ground and go forward. So there are some ideas there. Some other trends for metro, the standard in the world is single track double tube, which is 6.5 meter roughly diameter, with the platform in between, or 9.5 meter diameter is, pretty much the standard for double track single tube, right? However, installation and excavation of the stations has become an issue because you have to do it cut and cover, and if you want to do it with tunneling, you have to do conventional sequential excavation method and so on. It's very slow. So there are a couple of projects that have considered to go 12.5 meter diameter, so that instead of platforms at the same level, the platforms are stacked. So you can actually have access to the platform, right? And this means that you drive the tunnel wherever you like, you can actually tap and have a station there without really heavy construction of the stations before or after. You can actually see the only thing you need to do for the station is to offer escalators or elevators to get to the platform level, and you can have your station anywhere you want, which is a huge advantage. So we're going from this system to this system. And of course, between the station, you can have, cross passages between the lanes if needed, because of course in metro operation, you need to sometimes cross the lanes for accidents, for repair, or for other purposes. In between the stations, you can actually change elevation and have cross passages as well. On-site first assembly of TPMs have started. This is for larger machines because the typical operation is that you order the machine, they manufacture it, you test it in the factory, and then disassemble it, move it to the job site, and run it, right? This factory to job site assembly is about 3 months at least, right? The shipping, assembly, preparation. So some of the projects to gain the time, that 3-month time, which could be crucial for the project, they ordered, they designed the machine, ordered the parts, ship it directly to the job site, and assemble the first machine on the job site for the first time and operate. So that gives you about 3 months or so. It was used in Niagara Falls machine, in Georgia, and a couple of other projects. One of the challenges in tunneling is, knowing what is ahead of you. So there has been a lot of effort for past 30 years to come up with a system that could see the fault zones ahead, or in the soft ground, if there are obstacles, rock blocks or boulders to identify, because if you hit it, you've already damaged the machine, it's too late. So prediction of the ground ahead is a major issue, big open topic for research as well. There are some microseismic and geoelectric systems that can actually do some work, but we don't have a solution yet. This is a picture I took in April. Operating in gassy tunnels is a challenge. Gassy tunnels where you have methane or hydrogen sulfides and whatnot. Methane is explosive, especially at about 2 to 5%. It becomes the threshold of lower explosive limit is passed. So if you declare a tunnel gassy, the entire machine and the entire tunnel has to be retrofitted for gassy certified equipment. Very expensive and very complex to run. However, what you see here is the conveyor of the machine that has been enclosed for the entire backup. So as the muck comes out, and typically gas is released by the muck. So they put it on this on the conveyor in this chamber, and they can actually suck the gas out. So the rest of the tunnel, you operate normally. It's pretty neat, I thought. It was very good. What's happening with the machines, the sensory system are now huge. If you look at, this is one screen out of the operator's, multi-screen system. And if you pay attention down below, each tab is a different sensory system. So the machines are now coming up with a lot of sensory capabilities. I said from all the way from the cutter head to the back end of the machine, pretty much anything that happens, the operators can see. And this picture, actually, let me go up, is the first machine that the manufacturer is claiming to be operated by AI. This happened during our site visit to Shenzhen earlier this year in April. The machine is 13.5 meter diameter, single deck, double track, two-track road that they're making. And if you stand in that section, you see you're right behind the cutting head and the machine here. On the left-hand side, they had this multi-panel screens. On the right-hand side, exactly opposite to it, within a couple of meters, is the operator cabin. So you can see the operator is running the machine, but you could see what the operator is doing on the larger screen. However, you could actually see the machine running. Let's see if it works. Anyway, for some reason it's not working. But you could see that the machine is running and operating, and if the operator decides to walk away, can push the button, walk away, the machine would run by AI, meaning that the AI has already monitored the operator in different grounds, different sensory system, and learn how to deal with the machine, with the ground. Even if the operator is not there, it can actually operate. So this is claimed to be the first machine that was run by AI. And not to be outdone, I've been actually pushing for using TBM even on the moon. This is the future. We're going to go back to space and on the moon. And we cannot have surface cities and facilities. We have to do a lot of underground work, and I maintain that you have to do it with TBM. That's the lecture I offered yesterday in Lahore, and you can actually look at it. Again, with that, thank you for your attention. Be glad to answer your questions.
Audience, if you have any questions. Yes.
Sir, first of all, thank you very much for this informative and
Sure.
presentation.
Let's wait for the microphone because the audience online may well hear the question.
Sure, thank you. First of all, thank you very much for this amazing presentation. It was really informative. I would just like to know do we have any productivity charts for tunnel boring machines, like how we can determine the productivity?
Well, again, in soil tunneling, you pretty much have a set rate, say between 14, 15 meters a day is roughly the range, because excavation is not an issue. Logistic and ground support, which is by segmental lining, determines how fast you can go. And the norms in the world are in that range, give and take a few meters depending on the diameter. In hard rock, there are certain models that you can actually look at the rock properties, joint properties, rock mass properties, and estimate how fast the machine can go, right? And then through the logistics also and the precedents in the past, see what's the machine utilization and estimate the machine performance. I would say we can come as close as about, say, plus minus 20% of what the machine can do in rock as well. So we have developed the models over the years to do the predictions. So to give you a brief estimate, there are available models that can tell you how fast your machine can go. But nevertheless, whatever you do, as I said, is a lot faster than drill and shoot anyway. Sure.
Thank you so much for your detailed presentation. I'm very curious about the financial aspect of EVMs.
Right.
The thing is, in a countries like which are developing countries, where the cost of the product cannot be fluctuated that much. So, as you mentioned, that sometimes there are some unforeseen circumstances where you have to incur a lot of cost. So, what type of like financial model or what type of schemes are available to support this type of project?
Sure. Very good question. Okay. When we talk about a tunneling method dominating in the world, it has a hidden message. What is that hidden message? The hidden message is that this was the most economical way of doing it, right? So if you go between Pakistan, Iran, China, US, Canada, and so on, that threshold of using mechanized versus drill and shoot or conventional could be off by a little bit because of the workforce cost, right? However, and I was in Tehran last week giving a lecture. Actually, we had a workshop with some owners and engineers and so on. I mentioned that, listen, guys, if we go out of the norm, it may sound attractive from the financial point of view. However, we're losing a lot by delaying the projects. You know what I mean? There is a reason that you go to Qatar, which has probably, compared to you guys, has zero capability, technical capability. Are you with me? Compared to you guys, with all the talents you have, with all the capabilities, I can tell you very comfortably that a country like Qatar has zero capabilities. But they start the project, finish the project on time, and they reap the benefit. Billions of dollars, not millions, billions. How do they do that? They go with the international norm, they bring the best of the contractors, consultants, get the job done, and profit from it. Why is UAE or Qatar or these countries that have almost no technical capabilities using these systems, and they're so rich? There is a reason for it, right? So to give you an example, I remember about 25 years ago when I finished my PhD, returned to Tehran, they were digging up holes for the source system because Tehran didn't have a source system at the time. So they were going shaft to shaft, about 150 meters, connecting the two shafts and then putting the conventional and really labor-intensive manual work. So I started advocating the micro-tunneling system, pipe jacking. And I had a meeting with the head of Tehran's water source system. And when we were discussing the issues, he said, listen, what does a machine, a micro-tunneling machine cost? I said, about $1 million. Okay, fine. And with the inflation in Iran that was around 30%, he said, well, this means that if I buy a machine for $1 million for the first year, the cost of capital is about $300,000. And yeah, he said, well, listen, I can do the whole project for $300,000. You know, that was the mindset. However, this is the problem. If you go with that mindset, which from the look of it, it looks very attractive and it is justifiable, the reality of it is that the project is typically behind the schedule. The end product is really low quality. And you do that cost, in 5 years, you have to go back, dig it up and repair it. Think about all of the projects that we do collectively, right? Iran is pretty much like Pakistan, right? We spent a lot of money duplicating the work and a lot of lost opportunities because of the delay. I mean, think about the project like Nil and Jila, right? From what I understand, you're talking about 4,000 megawatts. What is the economic value of that per day? Right? In millions. What if you delay the project by 2 years? What is the lost benefit of that project? And so we often make, this mistake of thinking that, oh, well, the capital cost is high, I'm not going to do that. But we are losing in big picture. One thing also I have to mention that is very critical. Any of the machines that I talked about here, the cost of it is in millions of dollars. A typical, let's say, Metro 6.5 meter diameter machine is about $20 million. It's a big number, right? You tell that to a lot of owners, they go like, wow, there's a lot of money. You know what? That $1 million compared to the cost of the whole project is typically between 5 to 10% of the whole project. So is it logical to compromise 90% of the cost for being scared of the 10% initial capital investment? You know what I mean?
Yes.
And in reality, the reason that Europe or US or some of these countries are making progress and they're rich per se economically is that they do it right, they do the right investment, and the benefit economic turnover makes up for the whole thing and 10 times over. To give you a quick example, I remember back in early 2010s, Dubai was doing their monorail project from metro, from airport to the spine of the what is it, Charles, as you know, whatever the main spine. And they did the contract, design, build, and actually turnkey project for $16 billion, including underground work, surface work, and so on, to a consortium of Japanese and a couple other countries. And the joke was, at the time, that the estimate for the job was 14 billion, and what Dubai offered was around 16 billion with the incentives. So estimate was 14 billion, they offered 16 billion with the incentives. And a lot of people in the construction industry are laughing, well, why did you actually spend another $2 billion? What the hell for? Here's the catch. The project was finished on time and ahead of time. They proved that they can do this capital type of projects, and the real estate they sold along the way was $50 billion. So who is laughing now, right? Think about it. Initially, they think that they overpaid by $2 billion. The reality was that at the end, they gained multiple of that in real estate and economic turnover, right? So when we talk about the machines, don't let the initial price tag scare you, because ultimately it's about 5 to 10% of the total project. Don't compromise 90% for that 10%. That's the message. Sure. Right.
Thank you, Professor. Classic presentation as usual. Professor, you discussed about changing the diameter, variable geological composition of the ground. How about, changing the alignment, specifically if we're concerned about the micro tunnel, whether it be for, sewer tunnel, strong tunnel being done with pipe jacking method, and beside that, if there's, medium-sized tunnel involved with, mixed run. So, how are the advancement about the best of the best radius observation that we can achieve with those TVUs, about the observation?
Your focus is on the diameter change or the change of the machine?
The actually changing the alignment like in different sort of tunneling, micro tunneling, large size tunneling, medium size tunneling, like how the best we can achieve the smallest of the smallest radius observation. If we need that, there are some particular cases.
Changing of the alignment actually has happened typically as a consequence of the field observation. Like the Niagara Falls machine, they had an alignment, they had so much collapse of the roof, they had to go about 5-10 meters below to go to a better rock. Now, this happens, it's not unusual. However, the key is not changing of the alignment or changing of the machine or radius. The key is back in the design stage when you do alignment selection. Look at the different alternatives. Make sure that you pick the right alignment and you develop what's called the right packaging. See, packaging means what? If you have a very long tunnel, you go from rock to soil and back to rock and so on, you could actually sink shaft and separate the sections if it's warranted, right? So trying to do the whole thing with one machine, okay, technically can be done, but it's very high risk. So one of the things that we do when in the US when we design a project, we talk to the owner and see what is their capacity for risk. If they want lower risk, we opt for separating the sections of the alignment for separate machines. It's higher cost, we know, but what's the consequence? It's lower risk, right? So by the time you put the package on the street and bid on it, and the contractor mobilizes, bring a machine, if you want to do changes too late, it's too expensive. So it's better, as they say, measure twice, cut once, right? So if we do it right with the geotech information, with the construction, knowledge of construction, and value engineering, meaning what? You look at 4 or 5 different alternatives and do cost estimation, do risk assessment, and choose the one that fits your client best. And that would actually work the best as far as alignment, turning, changing diameters, or changing dimensions.
I think we are very short of time. There is only one question I will ask Dr. Islami from online. In rock-burst conditions, is there any advancement in TBMs to install separate drilling systems to drill stress relief holes or probe drilling within the TBM technology? So for the rock-burst, they are asking for the probe drilling. Is there any advancement in that?
Okay. Rock burst. Again, to do it right, you have to deal with the issue at the geotech investigation time. If you do the geotech investigation and you know that you have high stress conditions, you have to have special provisions in the machine to deal with it. There are cases like this Argos project or Seymour Capilano, Vancouver, Yangtze River. They didn't actually do a proper assessment of the stress field by the time the machine was in. I shouldn't say they got surprised, but they were surprised. Part of it is that the stress distribution in the ground in longer tunnels is not necessarily uniform. You might do a stress measurement and come up with a lower number that is actually happening in certain part of the tunnel. Nevertheless, probe drilling is not going to help you much with the stress conditions. Probe drilling is for fault zones and for water. But if you want to deal with the stresses, there are some studies that show that if you do a series of holes around the tunnel, the ground becomes softer and spongy, and you can actually pass through without much of an issue. It would reduce the rock burst impact, right? Running through rock burst is still a problem in the world. It's not solved. But worse than rock burst is the opposite of it, which also is critical, which is ground squeezing. In high stress ground, in softer rock, you may encounter ground squeezing. That's even worse than rock burst. So either one, I co-advised a student recently in Leuven University in Austria to develop what's called a cumulative risk index in high stress conditions to see what is the risk of a rock burst. Because if you go with shielded machine, you can probably deal with the rock burst a little bit better. However, shielded machine in the squeezing ground is a kiss of death. I mean, it can actually get trapped. So developing a cumulative risk index is a way to do. But with rock burst, we don't have a definite solution. Hoping I answered the question clearly.
Yes, I think there are a couple of other questions, Dr. Khan. I don't think so. We have time now.
Okay.
I think there is a PTTS who wants to announce their own platform here.
Sure.
So thank you very much for your this lecture.
Absolutely.
Assalamu alaikum everyone, and thank you Dr. Isaac for giving me the chance. I will not take so much, just a couple of minutes to introduce ourselves. We are Pakistan Tunneling and Trenchless Society. Our secretariat is in Tunneling Institute of Pakistan in Shahapadiam. We are the face of Pakistan at the International Tunneling Association. We are doing some technical workshop, tunnel talk series, and all the rest of the fun and entertaining things for the young tunneling professional. We have our young member group where you can join us. Our communication secretary, maybe he is one of your university fellow, Ajib, he's sitting there. Please do call with him to become the member of the society. This society is also registered with Pakistan Engineering Council as a professional engineering body. Please join us for all the future research and development and training programs that we organize on regular basis. It's a wonderful opportunity on national level as well and international as well. So thank you for giving me the opportunity to introduce the Pakistan Tunneling and Trenchless Society at this forum. Thank you.
Oh, you